All right, so we're going to do an example of a chi-squared test of independence, hypothesis test. We have this question. It says one categorical variable has two groups, A and B, and you can see they're represented here. And another categorical variable has three groups, R, S, and T, and they're represented here, R, S, and T. The results of 502 respondents are summarized in the contingency table below. This is the observed contingency table. And so over here, we're going to do the expected values contingency table. And it says conduct a chi-square test of independence at the alpha equals 0.02 level. Okay. To determine if the first categorical variable, the one that's split up into A, B, is independent of the second categorical variable which is split up into R, S, and T. Okay. All right, so the first thing we're going to do is we're going to state the null and alternative hypotheses. So the null hypothesis is going to be the two variables are independent. Okay. So two variables are independent, and then the alternative hypothesis, H sub A, is going to be that the two variables are related. There are a few ways to say that. That's one way to say it. The two variables are related to each other, but we're just going to say are related. Okay. All right, so that's step one. Step two, we're going to identify the alpha, and it just set it up there. It says that the alpha is 0.02, and so that now allows us to do the rejection rule, which is going to be reject H sub O if the p-value, if p is less than the alpha, 0.02. That's still not that. There we go. Okay. Then we're also going to identify the degrees of freedom. So the degrees of freedom are going to be the number of columns, which is 3 columns. Okay, so it's going to be 3 minus 1 times the number of rows, which is 2 minus 1. 2 minus 1. So 3 minus 1, that's 2. So 2 times, and 2 minus 1, that's 1. 2 times 1 equals 2. So the degrees of freedom are 2. Let's clean that up just a little bit here. So our degrees of freedom for this particular chi-squared hypothesis test are going to be 2. Okay. All right, moving on to step 3. Step 3, we're going to create the expected values contingency table and complete the sums. We got to sum the rows and the columns here on the observed. So 63 plus 81, well, that's going to be 144. 79 plus 95, let's see, that's going to be 174, okay? And then 102 plus 82, that's going to be 184. Now, let's see if this works out, because it says there's 502 respondents. That means that this should be 502, but let's make sure. Let's go to our calculator and do 144 plus 174. 144 plus 174 plus 184. 184, and that gives us, sure enough, it's 502. Okay. And now let's do 63 plus 79 plus 102. That'll give us our first row total. 63, 79, 102. 63 plus 79 plus 63, 79, 102 plus 102. And that gives us 244. So we'll put 244 here. And then 81 plus, plus 95 plus 82. 81, 95, 82. 81 plus 95 plus 82. And that's going to give us 258. 258. And sure enough, if you were to add these two numbers together, you would get 502. Now we're going to carry these column totals over to the expected values table. So we're going to do 144, 174, and 184. And we're going to carry over these row totals, which is going to be 244 and 258. And we're also going to bring over the sample size, which is 502. Now, to get these expected values, we're going to do the column total, which is 144 times 244 divided by 502. All right, so let's go to the calculator. We're going to do 144 times 244 divided by 502, and that gives us 69.992. So here we're going to put 69.992. Okay, and now here, you know what I'm going to do? I'm just going to do the 144 minus this. Now watch how I can do this in a calculator. I can do 144 minus, and then I can just hit the answer button, because the number I'm subtracting actually was the answer from the previous line, and therefore if I just put minus answer, it'll give me, it'll put in what that was. So I get 74.008. So 74.008, and if you add these two numbers together, you get 144. Now we're going to do this cell right here, okay? And the row total is 244, and the column total is 174. So we're going to do 244 times 174. So 244 times 174 divided by the sample size, which is 502, and we get 84.57. This, I'm going to change this 3 to a 4 because this 7 is going to round this 3 up to a 4. So 84,574. 84,574. And now I'm going to subtract this from 174, just like I did before. So I'll do 174 minus answer, that's the previous answer, and I get 89.426. 89.426. Okay? And now to get this right here, I'm actually just going to do 244 minus these two numbers. Okay? So I'm going to do 244 minus 69,992, 69.992 minus 84,574, 84.574, and I get 89.434, 89.434. Okay, and now this one here I can get in two ways. I can either do 258 minus these two numbers, or I can do 184 minus this number. Let's do 184. Do 184 minus the previous answer, and that gives us 94.566. 94.566. Okay, now we have our expected values table. That was step 3. Now moving on to step 4, we're going to identify our chi-square critical value. So chi-square critical value, we're going to go to the calculator, but we're actually going to go to distributions. We're going to go down to chi-square, and our degrees of freedom was 2, so we're going to say 2, enter, and then next. And now we're going to change it to a right tail test. So come down here, okay, and then we're going to come over here, and our alpha, let's try and remember what our alpha was. Our alpha was 0.02, there it is. So we're going to put in 0.02, and our chi-square critical value is going to be 7.824046. 7.824046. 046. And so now we're going to do the rejection rule for the chi-square test statistic. We're going to say reject H sub O if the chi-square test statistic is greater than our chi-square critical value, which is 7.824046. All right, and now we're going to move on to step 5. In step 5, we have to actually calculate the chi-square test statistic. And remember, the chi-square test statistic requires us to add up a bunch of things. And we said the number we have to add up is going to be equal to the number of cells in the contingency tables. And we have 1, 2, 3, 4, 6 cells. So we're going to have to do 6 separate calculations and then get 6 numbers and then add them all up. And the way we get that calculation is we do the observed value minus the expected value. We square that number and then divide it by the expected value, okay? So I'm going to go ahead and write that all out now, but I'm probably going to speed it up a little bit. All right, here is our calculation right here, or this is our summation. Now we got to go and put it into the calculator. That I'm going to go ahead and speed that part up as well. Is everything keyed in? Now let's go ahead and hit execute or equals, and we should get our chi-square test statistic. Looks like we got 5.509231. 5.509231. So our chi-squared is 5.509231. 231. That's step 5. Now step 6, we're going to get our p-value that goes along with this chi-square test statistic. So we're going to go back, we're going to go to the distribution, the chi-square distribution. It looks like it's still here, chi-squared, our degrees of freedom is 2. We're still on the right side. So now, instead of putting a number in here, we're going to put our test statistic in here. And our test statistic is 5.509, so 5.509, 231, and our p-value is 0.063633. So our p-value is 0.063633. All right, and that's everything we have to do. That's step 6. Now we just have to make a decision. Well, there's 2 ways we can make the decision. The first thing we're going to do is we're going to compare the p-value to the alpha. Because look, the p-value has to be less than 0.02. Well, this is 0.06. This is not less than 0.02, and therefore we will do not reject. Do not reject H sub O. Now that's based on the p-value rejection rule. What about the test statistic rejection rule? Is chi-square greater than 7.824? No, it's not. Chi-squared, our test statistic, is 5.509. That is not greater than 7.824. Therefore, we do not reject H sub O. Okay? And this is an example of a full example of a hypothesis test where we do a chi-squared test of independence to see if the 2 variables, the one that has A, B as categories, is independent of the variable that has RST. And in this case, they are not independent, or excuse me, they are independent because we do not reject the null hypothesis.